second try. This time I hope I'll be more confident. Thanks for all the kind words and comments on my last presentation. Feels good that at least I did it quite right. So my next talk is about laser sail propulsion. It was a good a design competition by, yeah, let's get to that later. So I'll just, not interesting. Yeah, by I4S, the Initiative for Interstellar Study, founded in 2012 and now a non-profit organization in the UK. And they started a design competition about an interstellar laser sail propelled Starship to get international students on the project, work together to compete with each other. The idea is basically to keep the complex part of a system, the propulsion system, close to Earth, where you can maintain it, where you can update it, upgrade it, and have the ship, a less complex system, flying to the star system that you want to go to. And our boundary conditions have been that we reach the target system within a century. Our laser power, beam power should be below 100 gigawatts, and we should use near future technology. So how did we address that problem? We started with the laser. Where should we position it? We could put it on Earth. There's easy access, but we have atmospheric disturbances. We could put it on a satellite. That makes it highly flexible. Where you point it, we can use it for different future missions. But you require station keeping, which increases your costs. You need propellant. And we said, okay, let's combine the advantage of placing a laser of those two and placing the laser system on the moon. To reach Alpha Centauri, you have to be in southern hemisphere, so we put it on the lunar south pole. There you have no atmosphere, obviously. You don't need station keeping, and the moon is reachable with near-term technologies and in the near future. That's just the advantages and disadvantages, apart from the fact that it is difficult to put the 100 gigawatt laser plus the power system with 400 gigawatts somewhere. It is even difficult to put it on Earth, so not considering this difficulty right now. So then we said, okay, how to supply this system with power? One requirement was to use a space solar power. That doesn't sound good. Let's try this. Yeah, we said, okay, let's assume 40% efficiency, 250 gigawatts. That's a really large collector, 21 times 21 kilometer of solar collector. It is heavy and it is expensive. So our conclusion was it is not a good idea to do that with space solar power, at least with the technologies we have right now. But the alternatives, I don't know, maybe we'll have fusion power at some point that might be a good alternative to a power supply. Then we looked at the laser. They're basically just military lasers that fulfill our requirements, free electron lasers and diode lasers, because they don't need fuel that is used up. So that were the considerations. Just have a really robust laser system. That's why we just based it on current military technology. Next thing was we need an optical system, because like you know, I guess you know, laser beam diverges over distances, and if you're talking about interstellar distances, it gets more and more important to really focus your beam. One proposal that you can find in literature is Forward's Fresnel lens, 1,000 kilometer diameter. Our first intention was, okay, where do you put that? You have gravity gradients with that size that will just tear apart your lens. So we are going with smaller distributed laser arrays on the lunar south pole that can afterwards be reused for other missions, can point it in different directions, and it's easier to point them because the whole system is smaller, and this diagram just shows what the pointing accuracies should be when we want to accelerate at a certain distance in light years. And that's in the order of 10 to minus 12, 10 to minus 13 rads, which right now is not achievable, not from Earth, maybe on Moon, because there's no atmosphere, you can really try to point your system. But we are not experts in that, so we figured it's difficult. The next thing then was what kind of laser cell material do we use after we had the propulsion system. located on Moon. We need high reflectivity, low area density, and a high operating temperature, which sizes your which determines your minimum sail diameter to account for the 100 gigawatts distributed on the surface. We looked at the luminous mylar. That's too heavy, but it has a high reflectivity. We looked at pure graphene layers. They have a low density, really nice material, but a high transmittance. So basically everything goes through. That's why in the next step we looked at, can we have more layers of graphene? And from our basic analysis it works, so you have secondary reflections inside the layers and thereby increase the absorptivity and reflectivity. Like you see here with the number of layers, the force that you can put on that sail increases. But we also put alkali atoms inside to adapt the optical properties, but that made it heavier and the operating temperature decreased. But we found out that the minimal radius that could be achieved with just graphene is not optimal because it's very small, and to point at that and is not very optimal. And we also have a magnetic sail that I already talked about. And we said, okay, we want to reuse structures, take as few mass as possible with us, so we put a constraint on that. With all that technology and pre-analysis, we started to do a mission analysis. The standard phases, acceleration, deceleration, and the cruising phase in between. To reach our requirement, we need approximately 4.35% the speed of light. And then we started, and after acceleration was easy, then we had to use deceleration. We have a magnetic sail, I talked about that. The important part is that it is more effective at higher speeds. That means once you drop to lower speeds, your deceleration force just decreases to an amount where you cannot use it for 100-year deceleration, for a 100-year mission, sorry. So we looked at a different system, the electric sail, that's basically charged tethers that interact with incoming ions in the interstellar plasma. And it has an optimum at lower velocities. So we said, okay, in the next step, let's combine that. And we started with a magnetic sail, and when the acceleration of the magnetic sail would have been the same like with the E-sail, then we switched from magnetic sail to E-sail. And like you can see here with the blue line, the duration to decelerate is lower than just with an electric sail or with a magnetic sail. That's just a repetition of what I said. We said, okay, let's use the same structures. So the deployment beams for the laser sail also are there for the magnetic sail. And here you can see the results that we had gotten for spacecraft masses and mission duration. And we found out that we could use a design point with 4 tons of spacecraft mass. That's excluding all the sail masses, but the 4-ton spacecraft mass is not payload. So that's the whole spacecraft, and we assumed 12% payload fraction for that, which leads to 500 kilograms of really usable payload for scientific research. Just a few parameters. Our laser sail diameter is approximately 19 kilometers. Just to give you an overview of how large the ship is. And just short mission description that we came up with. Then we accelerate with the laser sail, seen in this picture. Then it gets disposed. We decelerating after cruising. We decelerate with the magnetic sail. Then we get rid of the magnetic sail and still have the E-sail for the last bit of the deceleration. And with that, we can make it in 100 years. And interesting fact, we go to 9% the speed of light with that ship to reach the 100-year. That's pretty awesome. And you hope that you don't hit anything at that speed. Okay, just quick for the subsystem, because we had to do a subsystem analysis. Power system was very difficult because we're in a long lifetime, but low mass. With Icarus, we gave it up to have low mass because the rest of the ship was just too heavy. We didn't even consider lightweight power system because that wouldn't have done anything to the overall design, but here, when you have only 4 tons of spacecraft mass, every kilo counts. So on RTG, when you take that with you, you need high initial mass due to the decay. Solar panels, you need the sunlight, laser light, but because have an electric sail that could be used as an electromagnetic tether, and by not charging it, the incoming ions in the interstellar medium would produce power for us. So we combined that. We have the electric tethers when we don't use it as an electric sail, and we use the solar cells when we don't have the electric tether. So we need power for deceleration, and for that we said, okay, we have 100 gigawatt laser, we just widen the beam and try to hit the spacecraft and transmit some power to that. Communication system, same as before, interstellar distances, large losses, so we need large antennas, but fortunately we had the structure of the laser sail. So one idea was just reuse the laser sail. For now we haven't gotten to that because we said we want to get rid of it. It has some mass and it helps us for deceleration. So we looked at the 2 standard options, laser and radio frequency. Some communication architectures like just directly sending it versus sending it from Earth, reflecting it at the spacecraft and sending it back, which would require less power at the spacecraft. But there you have just really high losses, so that was discarded then as not feasible. Or you put the large sail in between Earth and Alpha Centauri and try to modulate the light coming from the star. Sounded like a good idea in the beginning, but the signal-to-noise ratio that we calculated was just not good enough to get a signal back. So we stayed with the standard architecture, put a small laser system on top of the spacecraft and used that for communication. Just shortly about the payload. There are different science goals that you can achieve, just stellar observation, lander, and the ultimate goal, the search for life. So you would like to have telescopes, orbiters, and landers. Our conclusion was it's difficult to miniaturize some of these systems. That was one of the ideas in the competition to combine laser sail propulsion with CubeSats. But so far we don't have a CubeSat-sized planetary lander that fits in 500 kilograms payload. So we said for first mission, we just send a telescope that observes the system and have some small nanosatellites that swarm, like a swarm that you can send to interesting areas in the target system, like shown here. So we don't know yet if there are planets. We've seen some. We don't know where exactly. That will change over time, so the mission has to be adapted. And once an interesting region is identified, we would send the sub-probes there, the CubeSat probes. Okay, that just shows our system again. So we have here the communication system, laser, that's the telescope, I guess, or some thrusters. Basically, yeah, that's to our conclusion. For such a long duration mission, high scientific yield is required, and that's not feasible with the assumptions we had been given and that we had made. So we would need a larger spacecraft, but like you see here, with the mass increases, the power increases, and that's in the region we looked at. It's close to linear, so we would need really high power laser. But our conclusion was that we would have to increase the mass by 1 order of magnitude, but increasing from 100 gigawatts to 1,000 gigawatts beam power with then 2,500 gigawatts of real power that you have to provide, that was, in our opinion, not feasible. So the final conclusion was that we have miniaturization problems and also pointing requirements that we cannot fulfill. So the whole concept should be revised. That was our recommendation to I4IS. So thank you for your attention.